Good morning. It's a pleasure to be here. I want to tell you really very briefly about some theory that we've been developing in the last maybe 5 years, which is actually based on ideas that were born already in the 80s. And it's really a very long pursuit, which I believe is something which gets closer to what we all want, which is an interpretable deep neural networks, or something which we can actually understand. And I always have to quote this to this type of audience, that nothing is more practical than a good theory. And we really need it in this domain. So you all know that I hope that artificial intelligence really started as in the first phase of AI, which was essentially based on logic, expert system, and lookup tables. It went through a very significant phase transition in the 80s, where we moved from logic to statistics, and from lookup tables to curve fitting, essentially. High-dimensional regression problems or curve fitting, which is essentially all that machine learning was until about 10 years ago, when this idea of neural networks came back in this new form that we now call deep learning, with many, many layers of neurons, and I'm sure that all of you know something about it or use it all the time. Now, the real question is, so we all know that the deep learning approach is essentially just feeding, let's say, an image in this case to the first layer of these very simple elements of linear threshold functions, what we call the neurons, which are just mimicking in a very crude way the biological neuron. And eventually, through this cascade of layers, the representation transforms such that eventually, by back-propagating the arrows in this case, just taking the arrows of the label and using the chain rule of derivatives, essentially move it layer by layer to through the network, we eventually get very good machines that seem to perform, as we just heard, close to human performance, at least in some cases, both in image recognition, in speech recognition, in video, in language understanding, and in control, and you know, all the way to autonomous vehicles and so on. So the real question is, or the real surprise was, let's say about 10 years ago, a surprise to everyone, including the people who invented this method, that it works so well that nobody really understood why it works so well and what's really going on inside. So I have very little time to really tell you the full story, but essentially we have been combining three basic ideas that are all revolutionary in some sense. The first one is really that we have to forget about all we know about learning theory, and we have to move from what I call rethinking statistical learning theory, move from what computer scientists love so much, worst case distribution-independent bounds, to what I call typical behavior, problem-dependent bounds. And once we get rid of this idea of worst case behavior, we really understand that when we do vision, when we do image recognition, when we do whatever thing like this, we really care about that typical behavior, not about the worst case behavior. I really don't care if a very distorted image of mine is not recognized. I care that the typical case will be recognized. And the biggest difference between the 80s, when neural networks were first used seriously, and the late 2000s, is that the size of the problem grew up by 3 or 4 orders of magnitude. Essentially, we moved from 300 pixels in the image to megapixels. This is a very big, a very significant difference, and it brings us back to theories which deal with large-scale typical behavior. And the prototypical theory of this type in engineering is information theory. And actually in physics, it's more like statistical physics or statistical mechanics. That's where I come from, and that's where we started to work on these things 30 years ago. And now all these ideas are coming back, and that's really the beauty of it. But what is really important is that there's some sort of conspiracy, which I'm going to explain in a few minutes, between the structure of the network, or those layer by layer decomposition of representation, and the way we train them, using what we call stochastic gradient descent, which essentially these small changes in the weights which propagate backward through the layers. And it turns out that these two things work together in a very synergistic way, such that exactly this type of backpropagation of error, this type of stochastic small changes of the weights, push us to optimal performance in a very interesting way. And I think we really begin to understand this. So I just want to remind you that when we talk about machine learning until deep neural networks, it was mostly this type of question. I mean, how do we fit functions in high dimensions to empirical data? And you all know, of course, that it's not really important to fit all the data. It's important to find some simple representation which will avoid overfitting or will generalize well. So the issue is not fitting the data, but generalizing to new data, which is not part of my training data. This is really very important. So we are really trying to, what we say, opening this black box of deep neural networks. And essentially, I just want to get you one basic idea. I'm thinking about one slightly different way of thinking about the whole thing, which I call the information flow through the layers. So think about the first layer here, which I denote here by X, as the input, let's say, image, the pixels of the image. So this is a very high-dimensional random variable, which has a lot of variability, as we say, a lot of entropy. I mean, it's really very uncertain with a lot of variability, whereas the label, I call it Y, can be just one pixel. Is it me or not me? Or is it a dog or a cat, or is the car hitting me or not hitting me? Or essentially, we can always break it into very simple yes-no questions, and these are the labels of the problem. So now what happened, now the first radical change that I make to this picture is instead of thinking about the neurons, those elements, as single variables, I look at the whole layer. So hidden layer 1 is age 1, hidden layer 2 is so on, and the whole layer is one variable. And then I think how much information is actually flowing from the input to the output. So essentially you should think about it as something like a leaky pipes or tubes that are connected to each other. And essentially each layer is just like another tube like this. And then I push the information, which looks very much like fluid or incompressible fluid that goes through the network. And in each of these pipes, some of the information is going away. And only the relevant or the important part of the information survives. You can also think about it as a cascade of filters. I mean, each layer filters out some of the information and keeps only the most relevant one, such that eventually the last hidden layer preserves only the one bit in the picture which is really important for my identity. And the question is really, how does it happen? I mean, this looks like a miracle because there's no one pixel or one bit in the image which really tells me this is me or not me. It's all over the place. It's highly distributed. So how is this filtering of the relevant information really works? And essentially, we have a beginning of a very comprehensive theory of what happens there. And I want you just to take out two concepts. One of them is that the map from the input layer, to one of the hidden layers, let's call Ti in this case, I call it the encoder of the layer. So this is really the map from the input to the layer. And so each layer is characterized by two things, by the encoder, the map from the input to the layer, and by the decoder, the map from the layer to the output. And my quite striking statement that out of those millions of variables that we have in the networks, all the weights, only 2 numbers per layer are really important when the network becomes very large, in this large-scale learning that we all do. The 2 numbers are the mutual information of the encoder and the mutual information of the optimal decoder. Now, I'm not sure all of you remember what mutual information is. So just think about it, about how many of the bits that are in the input are really preserved in the layer, and how many of these are actually used to predict the label. And I argue that these 2 numbers really tell you the whole story eventually. In order to convince you, I'm going to show you a small movie, which is essentially this representation. So the x-axis here is what I call the information about the input, which is in information theory is denoted by IXT, where T is one of the labels. And in the y-axis, I denote this I information about output. So it's very simple. How much information is about the input in the layer, and how much information is about the output in the layer. And what you see here are 100 different networks which are trained on the same with the same training data actually randomized, so it's different sets of examples for every layer, for every network, and different initial conditions. And what you see here is the initial configuration of the network. So in blue here is the first hidden layer closest to the input. So it has a lot of information about both the input and the output, so about 1 bit about the output, and 12 bits about the input, which is the size of this network. It's a very small network. And the last hidden layer, which is really important in orange here, is the last layer, which in this initially has very little information, both about the input and about the output. And the interesting thing is that when you start training it using backpropagation, this is what happens to the layers. So you see that this is actually quite remarkable, because all these 100 different neural networks, entirely different weights, they're all randomized differently and have different random examples and different order of examples. Everything that can be randomized is randomized. They actually move very much together in this plane. And if you see that the trajectory that they make in this plane is really very interesting. During the first about 300 epochs of training, cycles through the data, they come up very quickly to about half of the information about the label. So half of the information about the label is not very good generalization. It's not very good training error, generalization error. And they all come together. The first thing which is really striking is that they cluster, they what we call concentrate in this plane. So all those different layers look like one point, and the larger the network, the more concentrated this picture is. But the interesting part is that the first 300 layers, you do essentially what I call memorization, or just fitting the training data. But most of the training is in the second phase, where it takes from 300 to about 10,000 epochs in this case. And you see that what happened there is that you slowly move upward, which means improving generalization, and to the left, which means forgetting the details of the input, or compressing the input. And notice that at the end of this, the last hidden layer is pushed to this very interesting point, which means that it remembers essentially 1 bit about the input, which means forgot all the details, only 1 bit from the input, and exactly 1 bit about the output. This is what we call in statistics minimal sufficient statistics. It remembers only what it needs to remember and nothing else. But in order to get there, the last hidden layer actually is using all the other layers. All the layers are actually moving to the left and forget information. If you just want to look at the summary of this, this is the picture I wanted to take home. Essentially, all the layers are doing those interesting trajectories from A to B to C. They do this compression, essentially, not compression, fitting the data very quickly and also improving, remembering slightly more details about the input. But most of the work and the most interesting part of the work is happening from C to E, where essentially the last layer forgets much of the details of the input and eventually get to very good generalization, which is predicting the label essentially perfectly. And it happens layer by layer. Each layer is doing it, and each layer eventually ends in a different place in this place. This is layer 2, this is layer 3, and so on. And you see that they stop in different places. And the interesting questions that, of course, come out of these simulations, and we see it in many, many networks, in big problems, in small problems, with convolution, without convolution, with skip connections, ResNets, whatever you want. It's always essentially there if you look at it correctly. And there's a lot of ways of looking at it incorrectly, so I'm not going to get into it. So essentially, if you look at those traces, this is what I call the information plane representation of the neural networks. These are on the right here, you see the same picture I showed you before, but the color here is the number of epochs. So dark is small number of epochs, and yellow is a large number of epochs. And you see that the only difference between these two networks is the number of examples. So here we have 80% of the data, which means a lot of data, well-trained networks. And here I have only 5% of the data, which means under-trained, not enough data. And if you look at this X-ray, this information plane representation of the networks, you see that the first phase, which is up to this green line, is essentially the same whether you have a lot of data or few data. So the fitting of the data, fitting the labels is actually very easy. You can do it even with a small amount of data. But then what I call the compression phase, which is really the main improvement in generalization, that's where the money is, eventually, is actually not working well when you don't have enough data. You're actually going down on the left here, but if you have enough data, it's going up, and eventually you get to this interesting sufficient statistics point at the end. So why does it happen? So we actually understand pretty well what happens here. There's a very full-blown theory that tells us two things. First of all, the information about the label is really equivalent to generalization error. Okay, so the y-axis here is very clear. Higher information is better generalization. Okay, I always have to emphasize this. This is easy to understand. What is not easy to understand is what is the role of this compression. Why forgetting the data, the details of the picture is actually helping us. And this is something I really had a long argument to actually convince people. And we actually know that this is improving generalization. Essentially, we know now that the dimensionality or the complexity of the network is not the number of weights, nothing close to the number of weights. It's actually more like 2 to the mutual information between the input of the last hidden layer and the layer itself. Which means that the more I compress it, the simpler is my hypothesis class in some sense, or the simpler is the function I'm trying to fit. So that's really a remarkable thing. So the question is, how does it compress the representation? So there are two things that are really important in this theory. The first one is that in this plan, information about input, information about output, there is a limit. There is a theoretical bound, which is this black bound here, which can be calculated only from the properties of the problem itself, not from the architecture of the network. The architecture doesn't matter as long as it's rich enough. And what I argue is that eventually this stochastic gradient descent is going to push all the layers to be on this, or very close to this optimal information theoretic bounds. And information theoretic bounds means that nothing can do better. So if my layers actually go to this bound, they're optimal machines. Now, so actually there are many details here. I mean, what is the role of the finite sample? What is the role of the bound? But what is really important that if indeed the layers really get to this bound, nothing, not even an alien from outer space, can beat them on this data. This is the best you can do, including my human brain. So that's a very good result in the sense that I actually have an optimality theorem for deep neural networks. If they actually converge to this bound, they are optimal in the sense of sample size versus error, nothing else. And indeed, if you actually look at the network that we trained, you see the blue line is the optimal theoretic line, this information bottleneck bound, and you see the layers, those red crosses, each layer is somewhere very close statistically to the bound. So how do they reach the bound? So the interesting answer to this is coming from looking at the same movie that I showed you before together with the error itself. And you see that exactly at this point where the last layer, the orange layer is starting to move to the left, there is a knee in the training error. And you see what with this knee in the training error means that essentially the error is flattened. And this means that the average gradients of the error are very small. And when the average gradients are very small, something very interesting happens. The fluctuations of the gradients becomes large. And this is, again, a picture I want you to remember. So up to about 300 epochs, the signal-to-noise ratio of the gradients is very high, very clean gradients. So we do essentially a drift motion directly into this shallow minimum. But from this point, you see the standard deviation, which are those broken lines, compared to the mean, this is a log-log plot, becomes much larger, which means I'm talking about a very noisy gradients. And these noisy gradients are due to the mini batches and many other things that we do in the stochastic gradient descent. And eventually, during this phase, the weights start to diffuse, move like random walks, mainly random walk. And the interesting thing is that this random walk, this added noise to the weights, is exactly the thing that is compressing the representation because it reduces the signal-to-noise ratio of the irrelevant details of the picture, of the image, of the input. So that's the secret. This diffusion of the weights is compressing the representation. So we have a nice theorem, which we call the compression theorem, which really tells you how it happens and why it happens. But maybe the main new result of this, I don't want to go into details here, is that one of the predictions of this theory is that when you add more layers, surprisingly, you converge faster. Converge faster, I just want to show you this. This is the number of iterations that it takes to converge to a good solution as a function of the number of layers in the network. And the prediction of the theory is that this should scale like in a log-log plot like a straight line, or what we call a power law, where the exponent is very predictable. It's from the properties of this diffusion. What you see here in orange is the theory, and in the blue line is the actual neural network. And you see this really remarkable result. More layers converge faster, not slower. And this happens because the layers help each other. So this is just one of the predictions, which is completely surprising, that come out of this theory. There are many others, including what I promised at the beginning, an interpretation of exactly what each layer represents. What are the features that are encoded by each layer, which is really the holy grail of deep neural networks, so what we call an interpretable model. I don't have the time to talk about it, but I hope you have the interest at least to look at the papers and read more about it. So thank you very much.